Hi, I'm Jeff Nolan, President of HTP America, and welcome to the world of TIG welding. Today we are going to introduce you to HTP's line of inverter TIG welders, give you some useful information on TIG torches, tungsten electrodes, and shield gas, explain the controls found on our InverTIG 201, and finally give you a welder's eye view of the TIG welding process as it applies to both steel and aluminum. We have a lot to cover, so let's get started. HTP currently has 5 different TIG welders in the lineup. The InverTIG 130 DCL is a DC TIG stick welder, so it can weld steel, stainless steel, but not aluminum. The 130 DCL is a 130 amp machine, so it is capable of welding 1/8 to 3/16 inch steel depending on the application. The unit operates on a 25 amp 220 volt single phase circuit and only weighs 9 pounds. We start the arc by the touch start method, which is easier than scratch starting and less likely to cause tungsten contamination. You touch the tungsten to the work, the machine senses contact and starts the arc when you lift the tungsten off the work. One of the nice features of the 130 DCL is the ability to remotely control the amperage by a foot pedal. This is an especially important feature for the novice welder as it gives you more control of the weld puddle and makes your welding much easier. Gas flow is controlled by a valve on the torch. The InverTIG 130 DCHF is a 130 amp DC TIG stick welder which operates on a 25 amp 220 volt single phase circuit. 130 amps of power means that the 130 DCHF is capable of welding 1/8 to 3/16 inch steel depending on the application. The 130 DCHF will weld steel, stainless, 4130 tubing, but not aluminum. The 130 DCHF also has a remote amperage control by foot pedal. The 130 DCHF starts the arc by either touch starting or high frequency. High frequency is a high voltage, low amperage electric current that is produced with a very high cycle or frequency. To give you an idea, the frequency of a 110 volt outlet in your house is 60 Hz. The frequency of the HF wave is anywhere from 16,000 Hz to 1,000,000 Hz. The HF arc is like a spark plug arc. It jumps the air gap between the tungsten and the workpiece to get the arc started, so you don't have to touch the tungsten to the work. This really makes starting the arc much easier and is an important feature for the novice TIG welder to have. Additionally, this non-contact arc starting eliminates any tungsten contamination. The 130 DCHF also has a gas valve in the machine to start and stop the gas flow, so you don't have to worry about manually turning on the gas. The InverTIG 160 DC is a full-featured DC TIG welder. The 160 DC has remote amperage control by foot pedal, your choice of HF or touch starting, and a gas solenoid valve to control the shield gas. It also features the ability to operate on 110 or 220 volts, has a 160 amp output, so you can weld 1/4 to 5/16 inch steel, and a pulse feature to minimize heat input in thin gauge materials. The HTP MTS 160 is a multi-purpose welder. This unique machine gives you the ability to MIG, TIG, and stick weld. This is a 160 amp DC touch start TIG welder with gas solenoid valve. It operates on 220 volt single phase power and the amperage is adjusted on the front of the welder. The InverTIG 201 is a 200 amp AC-DC inverter TIG welder. The AC mode of the InverTIG 201 welds magnesium and aluminum, and you can weld just about any other weldable metal in the DC mode. The InverTIG 201 offers you several advantages over conventional transformer-based TIG welding machines. The first and most obvious are the size and weight. The 201 weighs in at 68 pounds and is about the size of a personal computer. The original sine wave transformer-based TIG welders are about the size of a refrigerator and top the scales at over 800 pounds. More modern square wave transformer-based machines are about the size of a small washing machine and weigh anywhere from 200 to 400 pounds. This makes the InverTIG 201 very portable and easy to fit in a small workshop. The second major benefit of the InverTIG 201 is it consumes up to 60% less electricity than a modern transformer-based TIG welder, while at the same time producing 10% more power. That's right, an InverTIG 201 will produce a full 200 amps of welding power on a 30 amp 220 volt single-phase circuit. You may not have to pay for a costly electrical upgrade to your shop. The 201 is what you would call an advanced square wave TIG welder. When welding AC, we are able to vary the AC frequency from 20 Hz to 200 Hz. Conventional transformer-based TIG welders have the AC frequency fixed at 60 Hz. Welding with the AC frequency set at 200 Hz allows us to focus the arc to a point, which concentrates the heat and minimizes heat input into the weld. The AC wave of the 201 passes through the 0 point so fast that high frequency is only used to start the arc and not necessary to reinitiate it. This minimizes HF interference. In fact, it is possible to do touch start welding in the AC mode. And the InverTIG 201 allows you to adjust the AC balance over a much wider range than conventional transformer-based machines, from 10 to 90%. A lower balance gives you more of a cleaning cycle, and a higher balance gives you more penetration. Finally, because of the ability to control the AC wave, it is possible to weld both steel and aluminum with one type of tungsten, and that tungsten will maintain a point even in the AC mode. With the arc jumping from a point instead of a ball, you get much surer arc starts and there is less arc wandering. The InverTIG 201 is truly the next generation in TIG welding equipment. There are two main types of TIG torches, air-cooled and water-cooled. An air-cooled torch is not really cooled by air, but is cooled by the shield gas. The benefits of an air-cooled torch are they tend to be relatively inexpensive and make the machine more portable than a water-cooled torch. The drawback is they tend to be larger than a water-cooled torch for the same amperage, and they do tend to run hotter than a water-cooled torch. One of the most common TIG torches is the 17 series shown here. This torch is rated at 150 amps with a 100% duty cycle. All HTP air-cooled torches feature a single cable design with very flexible cables. Compare this to a separate gas and power cable or a more rigid vinyl cable. The highly flexible cable design makes your welding easier and reduces hand fatigue. Another common air-cooled torch is a 9 series torch, which is rated at 125 amps with a 100% duty cycle. You can see the 9 torch is smaller and will get into tighter places. This is a 20 series water-cooled torch. It is rated at 200 amps with a 100% duty cycle. It is the same size as the 9 series air-cooled torch and uses the same consumables. A water-cooled torch has 3 cables: water in, power, water out, and gas. Water-cooled torches are generally connected to a water cooler, which provides a source of cool water for the torch. And the coolant is a non-conductive pump lubricant that also provides resistance from freezing to 10 degrees Fahrenheit, such as the HTP coolant. The benefits of a water-cooled torch are they tend to be smaller for the same amperage rating, and they stay cool. The drawback is they add cost to the machine, and when used with a water cooler, reduce the portability of the equipment. Now let's look at a few accessories for TIG torches. Here are Pyrex cup kits installed on the 17 series torch. 17S is the short kit, and the standard 17 kit is the longer one. It gives us the most obvious benefit of being able to see through the cup. It also gives us a benefit of being a gas lens. A gas lens will reduce turbulence in the cup, providing laminar flow of the shielding gas. This prevents turbulence from pulling the atmosphere into the shield gas and contaminating the weld. Using the Pyrex cup kit in conjunction with increasing the shield gas flow rate will allow you to stick out the tungsten further to get into a tight spot. Here you can see a gas lens collet body and gas lens alumina cup. These replace the standard collet body and alumina cup. They give you the benefit of laminar flow and allow you to stick the tungsten further out, but the drawback is they are larger. There are several other torches available. Here are a few of the more popular. This is a flex head torch. The torch head actually bends in any direction to get into tight spots. Another is the swivel head torch. This is nice for working with tubing. And this is a micro torch, which is ideal for getting into extremely tight places such as cylinder head ports or a collector as we have here. Now let's assemble a TIG torch. The collet body has holes that allow the shield gas to flow out from the torch head and around the tungsten. The collet body also has a hole at the front that matches the tungsten diameter. So if we were using a 3/32 tungsten, we would need a 3/32 collet body. Thread the collet body into the front of the torch and tighten snugly by hand. The collet is a 1 to 2 inch long piece of copper. It takes the welding current from the torch head and transfers it into the tungsten. Like the collet body, the collet is also matched to the diameter of the tungsten. You can see a slit in the collet, which allows the collet to grab the tungsten when the back cap is tightened. Place the collet in the torch so the slits will bottom against the collet body. There are 3 different back caps: short, medium, and long. The short and medium back caps are used to gain access in tight applications, so don't throw away your short pieces of tungsten. Long is the standard back cap supplied with most TIG torches and will accept a full 7-inch tungsten. Thread the back cap into the torch, leaving it loose. Place a piece of sharpened tungsten in the collet body. As you thread the back cap in, it pushes the collet against the collet body, locking the tungsten in place much like a compression fitting. Here is an example of a 9 series collet that has been over-tightened and overheated. It's always a good idea to have spares on hand so you are not down in the middle of a job. That is why HTP offers our spare parts kit, a great way to store your TIG consumables. Alumina cups have different sized openings, which are numbered and marked on the cup. The number corresponds to the opening size in 1/16 of an inch, so a number 8 cup would have a 1/2 inch opening. Thread the alumina cup on the torch. Remember, if you drop your torch, they can break. That's why the magnetic TIG torch holder is such a nice accessory. It always keeps your torch within arm's reach while preventing it from falling on the floor. If we loosen the back cap, it allows us to adjust or remove the tungsten. Tightening the back cap will force the collet against the collet body, securing the tungsten in the torch. There are 4 basic types of tungsten electrodes: pure tungsten, thoriated tungsten, lanthanated tungsten, and serrated tungsten. Pure tungsten is generally used on transformer-based machines when welding aluminum in the AC mode. Pure tungsten will tend to ball easily. We do not recommend using pure tungsten on inverter-based welders. Pure tungsten is designated by a green tip. 2% thoriated tungsten is the most common tungsten used today. It is generally used in the DC mode for welding steel and stainless steel. It provides excellent resistance from weld pool contamination and provides good arc starting capabilities. It does have a very low level radiation hazard, designated by a red tip. Lanthanated tungsten is a good substitute for thoriated tungsten to eliminate the radiation hazard. It is generally used in the DC mode for welding steel and stainless steel on transformer-based machines and can be used for both AC and DC welding with inverter-based machines. It has a low erosion rate and gives you excellent DC arc starts. It's designated by a gold tip for 1.5% lanthanated and a blue tip for 2% lanthanated. 2% serrated tungsten is an excellent substitute for thoriated tungsten to eliminate the radiation hazard. It is generally used in the DC mode for welding steel and stainless steel on transformer-based machines and can be used for both AC and DC welding with inverter-based machines. It has a low erosion rate and gives you excellent arc starts with good arc stability. Designated by a gray tip or an orange tip for 2% serrated. Why 2 colors? Gray is the international designation and orange is the AWS designation. For some reason they deviate on this type of tungsten. Since the InverTIG 201 is an inverter-based machine, we will be using 2% serrated tungsten exclusively in this video. Now that we have talked about different types of tungsten, let's look at the different diameters. Generally, there are 4 diameters to be concerned with when using a 200 amp welder: 40 thousandths, 1/16, 3/32, and 1/8 of an inch. The thicker the material you will be welding, the larger the diameter of tungsten you will use. The chart on the screen gives you a good idea of the correct size tungsten for different thicknesses and welding amperages. Trying to use a large diameter tungsten when welding thin material will result in hard arc starting and an unstable arc. Using a small diameter tungsten on thicker material will overheat the tungsten, causing it to melt and contaminate the weld. Also remember that AC balance will have a great effect on the tungsten diameter which you select. A lower balance, more electrode positive, more cleaning, will put more heat in the tungsten and will require a larger diameter. A higher balance, more electrode negative, more penetration, will let you get away with a smaller diameter tungsten. Tungsten should always be sharpened so the grinding marks run along the length of the tungsten or longitudinally, never radially. Radial grinding marks will cause arc starting problems and arc wandering. It is also important that the tungsten be sharpened on a clean grinding wheel that will not contaminate the tungsten. Preferably, this grinding wheel will only be used for sharpening tungsten. A very easy way to sharpen tungsten is to chuck the tungsten in a cordless drill and use the drill to spin the tungsten. Remember, always wear safety glasses. If you are unable to have a dedicated grinding wheel for sharpening tungsten, then you may want to consider the HTP tungsten grinder. This tool operates on 110 volts, is extremely portable, and gives you a perfect point every time. It is available in two models, a fixed angle and an adjustable angle. If the tungsten has been contaminated, use the tungsten grinder to cut off the tungsten prior to grinding. Then insert the tungsten into the grinder to sharpen. When sharpening the tungsten, the taper length should be 2 to 3 times the diameter of the tungsten. You can also use the tungsten grinder to flat spot the tungsten, which is removing the sharp point on the end of the tungsten to prevent it from spitting into the weld. The tungsten stick-out is the distance the tungsten sticks out past the end of the alumina cup. This can be anywhere from 2 to 3 times the diameter of the tungsten with a standard cup setup. Using a Pyrex cup or a gas lens and increasing the gas flow will allow you to get a stick-out of up to 6 times the diameter of the tungsten in a draft-free environment. In this video, the shield gas that we will be using is 100% argon. There are other shield gases available for TIG welding, such as helium and helium-argon mixtures, but they go beyond the scope of this video. Generally speaking, the flow rate will be 15 to 25 cubic feet per hour. This will be dependent on the diameter of the cup and the amount of tungsten stick-out. Not enough shield gas will cause weld quality problems, and too much shield gas can cause turbulence, which can swirl around and mix the atmosphere with the shield gas. Setting up an InverTIG 201 is very easy. The torch installs in the negative output receptacle. Just plug it in and twist it to lock into place. This is called electronegative in DC and has the flow of electrons from the torch to the work, increasing penetration and reducing heat in the torch. The gas supply hose from the TIG torch attaches to the gas output connection on the front of the InverTIG 201. Tighten snugly with an open-end wrench, but do not over-tighten it. Note that the sealing connection is made by the gas fittings, not by the threads, so use of Teflon tape is a waste of time and may only cause problems. The 3-pin trigger connection is used with a TIG torch that has a momentary contact switch. Since we will be using a remote amperage control, the 3-pin trigger connection will not be used. The positive output receptacle is where the ground cable is connected. Like the torch, plug the ground cable in and twist clockwise until snug. The 5-pin connection is for the remote amperage control. HTP has 3 remote controls available for the InverTIG 201: foot pedal, slider, and rotary. These allow you to remotely control the welding amperage while you are welding. If you are using a water-cooled torch, you will need to connect the water cooling lines to the water cooler. The chilled water out of the cooler is connected to the water in to the torch. The water in line is a separate line that runs directly to the torch head, supplying the torch head with cool water. From the torch head, the water flows down the power cable to cool it. In the twist lock connector, the water and the welding current get separated, and the water out goes back to the cooler through the water return line. This is the hot water out of the torch and the water into the cooler. Remember, cool water always goes directly to the torch head, and return water flows down the power cable. Let's explain what all the front panel controls do. Although specific to the Invertig 201, many of these controls can be found on other machines, so this may help you understand how to adjust your specific machine if you do not own a 201. When we turn the machine on, you will see the green power indicator lamp lights up. This indicates the 201 is connected to a 220 volt power supply. And the 201 only requires a 30 amp 220 volt single-phase circuit. The welding current lamp will be illuminated when there is welding current at the TIG torch or the electrode holder. This is when the foot pedal is depressed in one of the TIG welding modes, or if the unit is in the stick welding mode, the welding current light is always on. If the thermal switch light becomes illuminated, you have exceeded the duty cycle of the machine and it will not weld. Leave the machine on and let the cooling fans continue to run. When the thermal switch light goes back out, the machine will be ready to weld again. The welding volts display is a multifunction digital display. While you are welding, it displays the welding voltage. Pressing other touchpad buttons will display other parameters, which we will cover later. The welding amps display is also a multifunction digital display. While you are welding, this displays the welding amperage. Pressing other touchpad buttons will display other parameters, which we will cover later. It is currently displaying 004, which is the starting amperage for the machine. The AC welding mode controls whether the 201 is in the AC or DC mode. Depressing the button and releasing it illuminates the green AC light, indicating the machine is in the AC mode. Depressing the button until the green light goes out puts you in the DC mode. Remember, AC for aluminum and magnesium, DC for all other weldable materials. AC frequency is the number of times per second the AC wave alternates between electrode positive and electrode negative. The wave starts at 0, goes to positive 200 amps, back through 0 to negative 200 amps, and then back to 0. All this happens 60 times a second. This is a 60 Hz wave found in a conventional transformer-based machine. Adjustable AC frequency is one of the major benefits of the Invertig 201. The ability to adjust the AC frequency from 20 Hz to 200 Hz gives the welder much more control over the arc. We start at 200 Hz. You hear a high-pitched buzz. This is a completely different sound from a conventional transformer-based machine. The display is showing the frequency. Watch as we dial it down, ending with a low-pitched buzz at 44 Hz. Picture a garden hose with an adjustable nozzle. The 20 Hz wave is like a fan spray, very wide. As we increase the frequency, the spray gets narrower and narrower till it becomes a fine point. The concentrated fine point arc has the following benefits. Produces a more focused arc that results in a narrower bead. The heat is more concentrated, minimizing the heat affected zone, and it allows you to weld aluminum with a 2% thoriated, 2% serrated, or 2% lanthanated tungsten sharpened to a point. The arc is much more stable and less likely to wander. To adjust the AC frequency, simply turn the frequency knob when the machine is in the AC mode. The amps display will flash and display the AC frequency. The best way to explain AC balance is to look at the square wave graph. This is a 60 Hz balanced AC square wave. An AC wave is said to be balanced when there is an equal portion of the wave electrode negative, electrons flowing from the torch to the work, increasing penetration, and an equal portion of the wave electrode positive, electrons flowing from the work into the torch, providing more cleaning and putting more heat in the torch and the tungsten. An AC wave is necessary for welding aluminum because when the electrons are flowing from the workpiece to the torch, it helps float impurities to the surface of the puddle and also breaks up the aluminum oxide which forms on the surface of all aluminum which is exposed to the atmosphere. In certain instances, such as welding a thick piece of aluminum, we may want more penetration, electrons flowing from the torch to the work, so we increase the AC balance. And in certain instances, such as an oily casting, we may want more cleaning, electrons flowing from the work to the torch, so we decrease the AC balance. The balance control lets us change the percentage of the wave that is electrode negative. So let's look at this again. With the balance set to maximum penetration, which in the case of the Invertig 201 is 90%, 90% of the time the electrons are flowing from the torch into the work and putting heat into the work, providing maximum penetration. This is a piece of 3/4 inch thick aluminum. Generally, with a 200 amp TIG welder, you would not be able to get a molten puddle to start a bead. But with the Invertig 201, you can see with the balance at 90%, frequency at 200 Hertz, we have enough heat to get a molten puddle and run a bead. Now let's set the balance to maximum cleaning, which in the case of the Invertig 201 is 10%. 90% of the time, the electrons are flowing from the work into the torch and putting the heat into the torch. You have to keep in mind that when you change the balance, you are putting heat into the torch and also putting heat into the tungsten. At the same time, this is floating the impurities off the surface of the work and giving you more cleaning action. Let's see the effect the AC balance has on tungsten heat. We start welding at 60 amps with the balance set to 65%. A 1/16 inch tungsten works just fine. As we decrease the balance, you can see the tungsten starts to overheat and melt at about 40%, and by the time we get to 25%, it is fully molten. You can see how the melting tungsten has contaminated the last portion of the bead. If you reduce the balance, you may have to go to a larger diameter tungsten. You can adjust the balance when the machine is in the AC mode. Simply turn the balance knob, the volts display flashes and shows the balance in percent. The Invertig 201 allows you to adjust the AC balance from 10 to 90% over a substantially greater range than is possible with conventional transformer units, 40 to 60%. So remember, higher balance, more penetration, lower balance, more cleaning. The welding mode control lets you select one of several welding modes. In the stick mode, the machine is set up for arc welding. The 201 will let you vary the amperage in the stick mode with the foot pedal if you have the remote on and the pedal plugged in. The welding current is always on. The 2T mode is the most common. Push the foot pedal and the machine welds. Release the foot pedal and the machine stops. This will be the mode we will use throughout the video. The 4T mode is like a lock-on trigger on a drill and is used with the momentary contact switch. Push and hold the trigger for pre-flow. Release the trigger to slope up to welding current. Push and hold the trigger for slope down and post-flow. Release the trigger to stop. Do not use the 4T mode with the foot pedal. The TIG spot is for repetitive TIG spot welds. The machine will weld from 1/10 of a second to 10 seconds. This is set by adjusting the spot weld time. The program mode will allow you to switch between two predetermined amperages and is again used with the momentary contact switch. Amperage adjustment knob. This knob determines the welding amperage. The amperage on your Invertig 201 can be adjusted from 4 to 200 amps. The amperage is displayed in the digital display panel when the remote switch is off. When using a remote amperage control, the amperage adjustment knob is used to select the maximum amperage for your particular welding application. For example, when welding a 50 thousandths 6061 alloy aluminum, I want to limit the output of the machine to 100 amps. I turn the remote off and set the amperage to 100 amps. This is about 20% more power than I will need to weld the aluminum. I turn the remote switch back on and the digital display shows the starting amperage of 4 amps. If I were to depress the foot pedal completely, the maximum amperage would now be 100 amps. Setting the machine so the maximum amperage is limited to 100 amps instead of the maximum output of 200 amps makes the pedal less sensitive. More of a movement in the pedal results in a smaller variance of the amperage, making it easier to control the heat and therefore easier to control your puddle. Slope down is the amount of time it takes to go from the welding amperage to the final amperage. Generally, slope down is used in production welding with machines that weld at fixed amperages. The slope down time is adjustable from 1/10 of a second to 10 seconds. To set the slope down time, depress and release the slope down button. The volts display will flash SL for slope, and the amps display will flash and display the slope down time in seconds. While both displays are flashing, adjust the amps knob to set the slope down time. Using a foot pedal allows me to manually control the slope down with the pedal, so I have to set the slope down to the minimum setting, which is 1/10 of a second. This also adjusts the TIG spot time when the machine is in the TIG spot mode. Final current is the welding amperage the machine slopes down to. Depressing this button allows you to adjust the final current. This is only applicable when your InverTIG 201 is set in the TIG 4T mode, the program mode, or the pulse mode. The final current is adjustable from 10 to 90% of the base current that is set by the amperage adjustment knob. For example, if the amperage adjustment knob is set to 100 amps and the final current is set to 15%, the final current is 15 amps. To adjust the final current, depress and release the final current button. The volts display will flash FC for final current, and the amps display will flash and display the final current in percent. While both displays are flashing, adjust the amps knob to set the final current in percent to the base current. Remember, there is no final current adjustment in the 2T mode, since this is controlled with the pedal. Post-gas flow is necessary because after the arc is extinguished, if the gas stopped flowing immediately, there is a possibility the molten weld puddle would come in contact with the atmosphere, causing weld defects. Additionally, it prevents the tungsten from becoming contaminated by the atmosphere. The gas flow should run long enough to allow the orange color of the tungsten to disappear. It is important to remember not to remove the TIG torch from the weld until the post-gas cycle has been completed. A good starting point for the post-gas flow is 5 seconds. If you are welding at higher amperages or on more critical alloys, it may be necessary to increase the post-gas flow to a higher value. To adjust the post-gas time, depress and release the post-gas button. The volts display will flash PG for post-gas, and the amps display will flash and display the post-gas time in seconds. While both displays are flashing, adjust the amps knob to set the post-gas flow time in seconds. The post-gas flow is adjustable from a half a second to 30 seconds in 1/10 of a second increments. We would like to show you the effect of post-gas. First example is enough post-gas. 1/16 inch tungsten, red hot, cools completely while the post-gas is flowing. The second is not enough post gas. The gas stops and the tungsten turns black. If you have discoloration in your tungsten and you did not contaminate it by sticking it in the puddle or hitting it with the filler metal, then you are probably not running enough post gas. The pulsar alternately raises and lowers the welding current between the peak current and the final or background current. This is done a certain number of times per second, which is the pulse frequency. Furthermore, you can vary the amount of time you will be welding at peak current, which is the pulse duty cycle. Pulsing can reduce heat input on thin materials and give you better control of penetration and bead width. Using low pulse frequency can sometimes make it easier for the novice welder to time the addition of filler metal into the puddle. Depressing the pulse on button will illuminate the green light indicating your Invertig 201 is in the pulse mode. At this time, the volts display will show DUT for the pulsing duty cycle or the amount of time the machine is at the peak current. The amps display will show FRE for the pulsing frequency or the number of pulses per second. Whichever display is flashing is the one which can be adjusted by the amperage adjustment knob. If the DUT is flashing and you want to adjust the frequency, simply depress and release the pulse on button and the FRE display will begin flashing so you can adjust it. To adjust the pulse duty cycle, depress and release the pulse on button until DUT, which is displayed in the volts display, is flashing. When the display is flashing, adjust the amps knob to set the pulse duty cycle. Once the amps knob is turned, the display will change from DUT to display the duty cycle in percent. The duty cycle can be adjusted from 30% to 65% in increments of 5%. Again, the duty cycle is the amount of time the pulse is at peak current. To adjust the pulse frequency, depress and release the pulse on button until FRE, which is displayed in the volts display, is flashing. The pulse frequency is the number of pulses per second. While the display is flashing, adjust the amps knob to set the pulse frequency. Once the amps knob is turned, the display will change from FRE to display the frequency in hertz. The frequency can be adjusted from 0.4 of a hertz to 2 hertz in the AC mode and from 0.4 of a hertz to 300 hertz in the DC mode. Depressing the HF on button so the green light is illuminated turns the high frequency arc starting on. When the foot pedal is depressed, a high frequency arc will jump from the tungsten to the ground, initiating the arc. This makes it very easy to start the arc. Additionally, since the wave of the Invertig 201 travels so fast through the 0 point in the AC mode, the high frequency is used only to start the arc. Conventional transformer welders must have the high frequency on all the time to maintain the arc, which can cause interference. HF is a high voltage, low amperage electric current that is produced with a very high cycle or frequency. The HF arc is like a spark plug arc. It jumps the air gap between the tungsten and the workpiece to get the arc started so you don't have to touch the tungsten to the work, which eliminates the chance of tungsten contamination. When the high frequency is off, it is possible to do touch start welding. The touch start mode allows you to initiate the welding arc without high frequency. This is important in any environment where the high frequency arc will cause interference with sensitive electrical components or computers. A good example of this would be stainless steel or aluminum repair in hospitals. The touch start mode works for both AC and DC welding. In this video, we will be using the HF starting method. When the remote is on, the green indicator lamp will be illuminated, and the amperage is infinitely adjustable by either the foot pedal, rotary torch-mounted amperage control, or the sliding torch-mounted amperage control. This makes your welding easier by allowing you to control the amperage while you are welding. When the remote is on, the starting amperage is displayed in the amps readout. It is currently reading 4 amps. If you wanted to start at a higher amperage, push the remote on button. REM is flashing and displayed in the volts display, and the starting amperage is flashing and displayed in the amps display. While both displays are flashing, adjust the amperage adjustment knob to adjust the starting amperage to the desired setting. I will adjust the starting amperage from 4 amps to 25 amps. It is possible to limit the peak or maximum amperage of your 201. To limit the amperage of the machine to 100 amps, depress the remote on button for 5 seconds until the green indicator lamp turns off. You will see 200 amps in the display, which is what the machine is currently set to. Using the amperage adjustment knob, adjust the amperage to 100 amps. Depress the remote on button for 5 seconds until the green indicator lamp turns on. The display now reads the starting amperage, which we just set to 25 amps. Now, when you fully depress the foot pedal, the maximum amperage will be 100 amps. This makes the foot pedal less sensitive and makes it easier to control your pedal. Now I am going to set the starting amperage back to 4 amps. When the remote is off, the green light will be off and the amperage is adjusted by the amperage adjustment knob on the front of the welder. The machine will weld at the fixed amperage that it is set to. So now let's condense this into a quick setup. Welding mode 2T. AC. On for aluminum, off for steel. Frequency 200 Hz for aluminum, not applicable in the DC mode. Balance 65% for aluminum, not applicable in the DC mode. Slope down 1/10 of a second. Final current, not applicable in 2T. Post flow 6 seconds. Pulse off. HF on. Remote on. Ground plugged into positive. Torch connected to negative. 100% argon gas, 15 to 20 cubic feet per hour flow rate. Okay, let's start welding. First of all, don't try to TIG weld with regular welding gloves. Regular welding gloves are too thick and don't give you a good feel for the torch or the filler rod. Get a nice pair of TIG welding gloves like these HTP deerskin gloves. That brings us to filler rod. If you are buying rod in 36-inch lengths, make your life easy and cut it in half. This will prevent the end of that 36-inch rod from wobbling around and causing you to stick the filler metal in the tungsten. It's also a good safety idea to roll the end of the rod so you don't poke someone in the eye with the end of the filler rod. That is why HTP sells some of our filler rod in 18-inch lengths. You will also notice the rod is sealed in plastic tubes to help keep it fresh. Like tungsten, the diameter of the filler rod should be matched to the thickness of the work. Use a thin 035 or 045 for very thin sheet. MIG wire can even be used. 1/16-inch filler rod is a very common diameter and is good for sheet metal to about 3/32. Use a 3/32 rod for 3/32 to 1/4-inch material, and an 1/8-inch rod can be used for 3/16 and heavier materials. Second, it is important to be able to work the rod with your fingers. This is something you can do in your spare time, say when you are watching TV. Notice how I am doing this. Third, it is important to be as comfortable as possible when welding. I try to hold the torch like a pencil and steady my hand with the base of my palm or little finger. Try to hold the torch perpendicular to the work and incline slightly in the direction of motion. Welding steel. Once again, we are going to give you the basics for machine setup. 2T mode. AC off. Frequency not applicable in DC. Balance not applicable in DC. Slope down 1/10 of a second. Final current not applicable in the 2T mode. Post flow 6 seconds. Pulse off. HF on. Remote on. It is important to work with clean material. Acetone would be our first choice for cleaning the metal. If acetone is not available, lacquer thinner can be used, but it leaves a slight residue. Do not use brake clean, as the arc reacts with this cleaner to produce dangerous gas, which is very harmful and will make you sick. We will start by running a bead on 062 mild steel. Peak amperage is set to 80 amps, and we will probably be welding at 60 amps. Tungsten is 1/16 2% serrated. Before you can even think about joining two pieces of metal together, you want to become proficient in just being able to run a bead, without even putting filler metal in. The object of this exercise is to keep the tungsten between 1/8 and 3/16 of an inch off the work and move it in a very constant motion. TIG welding is all about the puddle and controlling the puddle. You do not start to move the torch until you can see the molten orange puddle. It should be about 1/8 to 3/16 of an inch in diameter. What you are looking for is a constant bead width and being sure you do not touch the tungsten to the work. When you want to stop welding, slowly lift the foot pedal until the arc extinguishes, and remember to leave the torch in the same position until the shield gas stops flowing. Here is the finished weld. You can see the bead width is very consistent, except for the narrowing about 1/2 an inch from the end. What happened is we skipped a little, increasing our torch travel speed, causing the bead to become narrow. You can also see a very consistent heat affected zone, and at the very end you can see the effect of the post gas flow. The shield gas continues to flow, protecting the weld from the atmosphere, preventing a color change. If we made this weld in a purge chamber, which is a chamber filled completely with argon, the weld would not change color. Since mild steel is not a reactive material like titanium or Inconel, and once the molten puddle solidifies, further cooling without the protection of the shielding gas will not affect the quality of the weld. When you have mastered running a bead without using any filler metal, can maintain a consistent bead width, keep your tungsten 1/8 to 3/16 of an inch off the work, and not touch the tungsten to the work, then you can progress to the next step in learning to TIG weld, which is to run a bead with filler metal. Before you can even think about trying to join two pieces of metal together, first you need to master running a bead without filler, and then you need to master running a bead with filler. Again, the key is in the puddle. You have to operate the foot pedal and control your torch so you can keep the bead width consistent. We establish the arc and gradually push down on the foot pedal to increase the amperage to start a molten puddle. When we have a molten puddle about 3/16 of an inch in diameter, start to add the filler metal to the leading edge of the puddle. Continue to dab the filler metal into the leading edge of the puddle. If you can dab the filler metal, say every 1/2 a second, just like a robot, at a constant rate, it will give you that nice row of dimes look. While you are dabbing the filler, remember to move the torch at a constant speed and height, and adjust the foot pedal to control the puddle and maintain a constant bead width. You dab the filler into the leading edge of the puddle. You can see the finished weld has a consistent bead width with a nice row of dimes appearance. Again, the heat affected zone is relatively narrow and also consistent. Remember, melt the filler by dabbing it in the molten puddle. Do not try to melt the filler with the heat from the torch. Practice running a bead with filler until it becomes second nature, making sure you don't touch the tungsten with the filler and you don't touch the tungsten to the work. When you have mastered running a bead with filler, you can try to join two pieces of metal together using the butt weld technique. A butt weld is two pieces of metal laid edge to edge. We are going to butt weld two pieces of 18 gauge steel together. 18 gauge steel is 48 thousandths of an inch thick. We will start by tack welding the coupons together so they don't warp. Depress the pedal to start the arc. Increase the arc by pushing the pedal further until you get a molten puddle, and dab the filler to make the tack. Repeat the process every 2 inches or so. Again, depress the pedal to get a molten puddle and dab the filler metal in. Keep the tungsten centered over the joint where the 2 panels meet and dab the filler into the molten puddle. Don't melt the filler with the flame of the torch. We are running about 50 to 55 amps. When you get to the end of the weld, gradually back off on the pedal until the arc extinguishes, and remember to leave the torch in the same position until the post gas flow stops. Look at this beautiful weld. You have an extremely consistent bead width with that very nice row of dimes look. Once you have become proficient in laying down a nice bead on a butt weld, the next weld to learn is the lap weld. A lap weld is where one panel is placed on top of the other panel. We will tack the panels together to prevent warpage. When you initiate the arc, keep the arc and the heat on the lower panel. The arc will always try to go to a sharp edge, so you may have to move the torch to force the arc to the lower panel. Get a molten puddle started on the lower panel. Then dab the filler into the molten puddle and get the molten puddle to wick up into the top panel. If you apply too much heat to the upper panel or let the arc start and stay on the upper panel, the edge will just overheat and melt away. The finished weld is a nice consistent weld. You can see the heat affected zone is also consistent. Fillet weld. The fillet weld is 2 panels at 90-degree angles. This is the hardest weld because it is very easy to melt away the edge of the upper panel. The heat should be concentrated on the lower panel using the molten puddle to wick up into the upper panel, similar to a butt weld. Let's watch. Again, it's all about controlling the puddle. The rod is again dabbed into the leading edge of the molten puddle. Here is the finished weld. Pulse welding is when the InverTIG 201 automatically pulses the welding current. The InverTIG 201 allows you to control the pulse frequency, which is the number of times per second the machine pulses, the pulse duty cycle, or the percentage of the time during the pulse that the machine will be at the higher welding current, and the final current, which is the current the machine pulses down to in a percentage of the peak current or the welding current. First, we are going to show you a slow speed pulse. We are set at 2 Hz or 2 pulses per second, a duty cycle of 40%, and a final current of 25%. A slow speed pulse can be used to help you time dabbing the filler metal. You can see we are dabbing the filler metal every time the machine pulses. It is important to note that you never want the duty cycle or the background current set so low that the molten puddle will completely solidify, as this may cause cracking. In the second pulse example, we have raised the pulse frequency to 200 Hz or 200 pulses per second. You can only hear the machine pulse, not see the actual pulses since they happen so fast. The duty cycle is 40% and the final current is 25%. This really increases our travel speed, minimizes heat input while assuring penetration. In the third pulse example, we have lowered the pulse frequency to 100 Hz. You can detect a different audible pulse, but again, you cannot see the actual pulses since they happen so fast. The duty cycle is now 60% and the final current is 25%. There is no set rule for adjusting the different pulse parameters. It depends on the specific application and the individual welder. By varying the pulse frequency, duty cycle, and final current, you control the heat affected zone, level of penetration, and travel speed. Even with material as heavy as a 1/4 inch steel, it is still necessary to tack weld the two pieces of metal together to prevent any distortion. We ran about 180 amps to tack this together. You will also notice we have beveled the edges of the material slightly to increase penetration. Remember, the technique is the same whether you're welding sheet metal or 1/4 inch steel. The difference is we have to put more heat into the metal, which means more amperage. By increasing the amperage, you will have to take into consideration the effect the amperage will have on the tungsten, so we increase the diameter of the tungsten from 1/16 of an inch to 3/32 of an inch. We are running close to 160 amps and adding more filler metal, but again, the basic process is the same. Isn't that one of the nicest welds you have ever seen? Consistent bead width, beautiful row of dimes appearance. This is a weld you could really show off. We start welding, going along fine, and then it happens. You wobble a little and hit the tungsten with the filler metal. The tungsten is so hot it immediately melts the filler metal. The color of the arc changes to kind of a bluish halo, and the shape of the arc changes from a cone to a sphere. By the third hit, you can see a large glob of molten steel on the tungsten, and the steel is melting off the tungsten, changing the arc and contaminating the weld. The only thing to do is to stop welding, remove the tungsten from the torch, cut the contaminated tungsten off, and resharpen it. Here is another common mistake. Let's face it, we have all done it. You are welding along, trying to keep your tungsten as close to the work as you can, and you touch the tungsten to the work. In this instance, the tungsten stayed in the puddle too long and extinguished the arc. The tungsten became stuck in the molten puddle when the arc extinguished and the puddle cooled. The tungsten must be removed from the torch and sharpened. Aluminum welding. Let's review a quick setup on the machine. 2T mode, AC on, AC frequency 200 Hz, AC balance 65%, slope down 1/10 of a second, final current not applicable in 2T, post flow 6 seconds, pulse off, HF on, remote on. Aluminum has some unique characteristics which differ from steel. Aluminum does not change color when it is hot or molten. The only way you can tell when aluminum is molten is the puddle becomes shiny. Aluminum forms an oxide as soon as it is exposed to the atmosphere. The problem with the oxide is it melts at 3200 degrees Fahrenheit, much higher than the melting point of pure aluminum, which is approximately 1100 degrees Fahrenheit. The oxide will form a film over the molten aluminum, so it is highly desirable to remove the aluminum oxide. The oxide can be removed with a stainless steel wire brush or a Scotch-Brite pad and then wiped down with acetone or lacquer thinner. When welding aluminum, the filler metal should be matched to the base metal as best as possible. However, in a repair application, many times we don't have the luxury of knowing what alloy we're actually working with. Generally speaking, 4043 is a good general filler metal for most welding applications. However, 4043 should not be used if the piece will be anodized, and a 5356 alloy should be used instead. Remember, 2000 series and 7000 series aluminum is generally not recommended to be used if the application requires welding, so try to stay away from those alloys. Use the following chart as a guide. The process for welding aluminum is very similar to steel. Once again, you are going to need to lay down a bead without any filler metal to start. You are trying to move the torch at a constant speed to give you a constant bead width and while keeping the tungsten between 1/8 and 3/16 of an inch off the work. One of the differences between steel and aluminum is aluminum does not change color when it is molten. It just becomes very shiny. So the only way you can tell when you have a molten puddle is when you see the shiny area. I could probably have done a better job. I should have cleaned the aluminum better. There was some type of residue on the piece causing a dark sooty area. As the piece heated up, this burned the residue off, which is why we don't see the soot as the bead continues. You can also see I failed to back the pedal off to compensate as the aluminum heated up and the bead is too wide, and then it starts to fall away from excessive heat. The last segment of the weld is very nice, very consistent bead width. I have picked up the travel speed and backed off on the pedal to achieve this. Once you have mastered a bead without filler, then you can try a bead with filler. Depress the pedal to start the arc. You need to look for the shiny puddle in the middle of the dull area. That's the molten puddle. Once you have the molten puddle, you begin to dab the filler in the leading edge of the molten puddle just like steel. Dab at a constant rate and move the torch at a constant speed to achieve that nice row of dimes look. Now isn't that a nice weld? Very consistent, nice in appearance. Remember, you have to practice, practice, and practice. Just a continuation of running a bead with filler, only now you are joining two pieces of metal together. As with steel, you need to tack the panels together. Once you get the panels tacked, you will now run a bead down the center of the panels, dipping the filler into the leading edge of the molten puddle. Remember, when you are going to end your weld, gradually back off on the pedal. This prevents a crater from forming when the weld pool solidifies. Also, leave the torch in the same position until the post-gas flow stops to keep the flow of argon around the weld until it cools. Here is the finished weld. I'm just a little inconsistent at the beginning, but you can see a pretty nice row of dimes look to the weld. Aluminum lap weld. This is trickier than a butt weld. You have to remember the arc will always be attracted to a sharp edge, so you want to initiate the arc on the lower panel away from the edge of the upper panel. As you increase the amperage, bring the torch closer to the upper panel, get a puddle going on the lower panel, dip the filler into the puddle, and again let it wick into the upper panel. Once the panels are tacked, the easiest place to start your bead is on a tack weld. Get a molten puddle and start moving. Again, dab the filler metal into the molten puddle. Here is the finished weld. You can see a little bit of contamination at the end of the weld. Again, we should have done a better job cleaning the panels. You can see there is a very narrow heat affected zone and a nice consistent bead width. Once you have mastered the aluminum lap weld, it is time to move on to the fillet weld. Again, remember to tack the panels. You will concentrate the heat on the lower panel and let the filler wick into the upper panel. Make sure you dab the filler into the molten puddle. As the name implies, you are filling a corner, so you are using more filler rod. You are actually pushing the rod into the puddle versus dabbing it. You want to put enough filler rod into the puddle to make a convex bead. We have increased the amperage of the machine to 160 amps to give us the penetration we need in the 1/8 inch aluminum. Also, with aluminum, since we are running in AC and putting more heat into the tungsten, we increase the tungsten diameter from 1/16 to 3/32 of an inch. Other than that, this is just like butt welding thin aluminum. The finished weld is nice in appearance and very consistent. Here we are doing a pulsed aluminum TIG weld on an outside corner. A good example of this would be an oil or fuel tank in a race car. We have the panels tacked together. It is a very good fit with no gap. In this specific application, we are able to lay the filler right in the crease and let the machine melt the filler and the two panels together. The machine automatically pulses between the welding current and the background current. The pulse frequency is set to 2 pulses per second. It really gives you a nice consistent bead appearance and minimizes heat input. Well, I hope you enjoyed our TIG welding video and gained some useful knowledge that will make you a better TIG welder. If you have any questions about any of our TIG welders or any of the products you saw in the video or in our catalog, please feel free to call us at 1-800-USA-WELD.